Let's start out by drawing a quadrant 1 graph. This would be the y-axis, this would be the x-axis. Let's draw a random curve. Let's go a little bit like this. Okay, let's put a line through that curve. I'll color it maybe red. I'm going to go through this point right here and this point right here. See if I can draw a straight line. Close enough. Again, if we need to find the slope, the only way you know how to do that right now is using 2 points, right? Well, let's develop those points. So for this, we'll call this C, x value C. And if this is f of x, the function f of x, what's the y value then? I understand where you're going with that, but not necessarily. I want to be more specific on this one. F of C, that's it. Okay, and I want to have another point over here, right? Another x value. But I want to go over a distance, a change in x distance. I don't know what it is right now, but I want to add on this distance. And I'm going to call that delta x. So what would this x value be then? Start at C, go over delta x. What would this be, you think? You bet. C plus delta x. So then this y corresponds to f of C plus delta x. Okay, remember C is an x value, delta x is the change in x values. This is the distance we walked over from C. And so we get C plus delta x. We don't know what it is, okay? All right, well, we can find the slope of this secant line. Slope of this secant line is equal to what? Let's go with, well, we need points, I guess, so we better make points. So this would be C plus delta x, f of C plus delta x. And this point would be C, f of C, right? Sometimes it's better to see the actual points than to pick out the x and y values for our slope because we're so used to doing that. All right, so y2, we'll call these the 2's and c, f of c the 1's. So we will have f of c plus delta x minus y1 would be f of c all over x2 would be c plus delta x minus x1 would be c. I think you guys see in the denominator we can simplify this. C minus c would be 0, so we just have delta x in the denominator. So we'd have f of c plus delta x minus f of c, and then we'd have delta x in the bottom. Obviously, if we knew what our c value was and our change in x value to get to the next x value, we could find the slope of the secant line given that we had some function f, right? Now, let's say we want the slope of the tangent line right here. I want the slope of the tangent line. And I better make that a different color. Let's go with maybe green. Let's say I want the slope of the tangent line right there. What do you guys think? Is this red line, the secant line, a pretty good approximation for the slope of the green line? I think we could do better, right? How could we do better? How could we get closer and closer and closer to this slope? What could we do with this red line or some points on that red line? What do you mean? What do you want to move? Well, what if C wasn't right here? What if C was right here? Would that slope of the new secant line be a little bit closer to the slope of the actual tangent line? What else could I do? Yeah, move this point closer and closer and closer and closer and infinitely closer to this point, right? If you did that, this red line pretty much becomes the green line, doesn't it? The secant line becomes a tangent line. So what would we want to change then? What would we want to go to 0? How about this guy, right? What happens if this delta x went to 0? I wonder if we have a way that we could let delta x go to 0. He was talking about already. Limit. So we take the slope of our secant line, but we let that distance between the two x values for those points go to 0, then we actually have a tangent line. So this would be the slope of a tangent line. Why is the slope of the tangent line? Because we're finding the slope given only one point. Questions on that so far? Is that kind of what you were talking about when you said limit? Really? Kind of? Okay. All right, you guys see if we let this distance go to 0, this one goes to here, and then we have our tangent line. All right, little book definition. I wouldn't write it all word for word because we have some of it already. Definition of a tangent line with slope m. If f is defined on an open interval containing c, which is an x value, and if that limit is the limit of delta x going to 0 of our change of y over change of x, and we have that limit definition of slope of a tangent line we already came up with. If that exists, then that line passing through CF of C is the tangent line with slope m. And when we say the slope of a tangent line, the other way to say it is slope of a graph at a point. That does mean slope of a tangent line. That's critical, you know that. It's important. We're not always going to say tangent line. If we say slope of a graph at a point, or what is the slope of the graph at x equals, say, 3, then we mean slope of a tangent line, and this is what you do. All right, examples. Sometimes we solidify the theory with the practical by doing some examples. Okay, what they'll say is find the slope of the graph of f of x equals 2x minus 3 at some point 2, 1. What is our c value that they're asking to find the slope of the tangent line at? What does c equal in this particular case? What's the x value of the point they want to find the tangent line at? That's just at 2. Yeah. Okay, in this case, our c is 2. What is our function? Well, they told us. And they told us the x value. They have to tell us those things, guys. Okay? So let's start out by writing out the limit way of finding the slope of a tangent line. Delta x goes to 0, and then we will have f of c minus delta x minus f of x. I'm sorry, c plus delta x minus f of c all over delta x. I was thinking ahead on some stuff. Sorry. Okay, c is 2. Plug in 2. So it'll be f of 2 plus delta x minus f of 2 all over delta x. They want us to find the slope of this line at some value. Okay, next step would be plugging in this function. And this looks familiar, right? I think you guys have done this already. You have done a couple problems like this already. F of 2 plus delta x means evaluate f wherever there is an x. You substitute 2 plus delta x. All right. 2 times 2 plus delta x minus 3 minus, and always being in parentheses, 2 times 2 minus 3 all over delta x. Notice how I'm writing everything out and I'm not leaving anything. I'm writing everything out. I'm not leaving anything out. Sounds weird. Keep going. Now it's just evaluating a limit problem. And again, we can't use direct substitution right now because there's only a delta x in the bottom. We cannot substitute 0 right at this point. So let's take care of the numerator. Let's expand and combine like terms, stuff like that, like we've done. Limit delta x goes to 0. So would that be 4 plus 2 delta x minus 3 minus 4 plus 3? And obviously you can just add these together. All right, we got 4 minus 4. We got negative 3 plus 3. That leaves us with Mr. Bonley, this is a lot to write. Yeah, we're going to spend the next like 4 chapters learning how to do this quicker. So we'll show you the long way that works every single time. Then we'll show you guys some shortcuts. Obviously, delta x is canceled. And we get to a good spot. What's the limit as delta x goes to 0 of some constant? What would this limit be? Just 2. What's the limit of the constant, guys? The constant. So, what does that mean? It means the slope of the tangent line, the slope of the graph at the point 2, 1 is 2. And why should that make sense? Why should the slope of 2 make sense? It's the slope of the graph, yeah. We found the slope of a line. So negative 3, 1, 2, 3, up 2 over 1, up 2 over 1. We found the slope of this line, right? Which this line has a slope of 2. So this line has a slope of 2 everywhere for every x value, right? They did in this one. And some people think about that. They see that right away. Well, this line has a slope of 2, so every point along this line should have a slope of 2, right? Because the tangent line to a line is the line itself, which intersects it in infinitely many spots, which is kind of breaks the rule of tangent line, but it is a tangent line. And that's kind of why I think sometimes they say find the slope of the graph instead of find the tangent line. Equation of the tangent line or slope of the tangent line. Okay, start off with an easy problem. Find the slopes of the tangent lines to the graph of f of x equals x squared plus 1 when x equals 0 and x equals negative 1. All right, it means we have 2 problems, right? We have 2 problems to do. Let's do the first one. So for 0, 1, we know c is equal to 0, right? And we know we can set up our limit. Limit as delta x goes to 0 of, are you guys okay if I say f of 0 plus delta x right away? Substitute 0 for c, minus f of 0 all over delta x. Well, that's just 0 plus delta x, right? So that's just delta x. And f of 0, we better leave that as f of 0. Okay, limit delta x goes to 0, f of delta x minus f of 0 all over delta x. Substitute now into the function. Limit, evaluate the function at delta x. That gives us delta x squared plus 1. Evaluate the function at 0. That gives us 0 squared plus 1 all over delta x. You're substituting delta x in. And any place you see an x, you substitute with delta x. All right, simplify the numerator. Okay, that gives us minus 1. So 1 minus 1 is 0, right? So we get delta x squared over delta x, which means a delta x and a delta x divided to 1. And all we are left with is that delta x in the numerator. Is it okay to let delta x go to 0 now? Can we use direct substitution? You bet. What's this limit then? This looks like 0 to me. What does that mean? The slope of the tangent line at x equals 0 to the graph of x squared plus 1 is 0. It's going to be extremely important to us later. Okay. Now, graphically speaking, that should make sense if we have the graph of x squared plus 1. And here's x equals 0. A tangent line would come across like this, right? What's the slope of that horizontal line? It's going to be 0, right? Do we get that? We're good? Okay. Well, part 2. Well, let's think about this for a minute. Since I have this graph up here already. At x equals negative 1, tell me something you know about the slope of the tangent line. It's what? Yeah, definitely going to be negative. So that's a quick way we can check our answer, right? So after we do this process, we should have a negative number at the end. Should it be like negative 100? I don't know if that's going to be, pretty close, but it's going to be negative. Okay, let's do it. For c equals negative 1, we're going to have the limit as delta x goes to 0 of f of negative 1 plus delta x minus f of negative 1 all over delta x. Now, what is this saying? We have to know that too, because sometimes they will give us an explanation and they'll say, what will allow us to find the slope of the tangent line at x equals negative 1? You have to know that this is how we find the slope of the tangent line at x equals negative 1. We have to know that. Okay, they're going to ask questions backwards. Okay, evaluate now. Limit delta x goes to 0. A lot of writing. Negative 1 plus delta x, quantity squared, plus 1. F of negative 1 would be negative 1 quantity squared plus 1. And notice how I'm using parentheses to surround this f of negative 1. More than one term. Make sure we don't make mistakes here. All over delta x. Keep me in line. Make sure I'm doing everything correct. Make sure I don't make a mistake. If you think I make a mistake, let me know.
Why do you square those things?
What do you mean, why do I square them? X is squared, and we're evaluating the function at negative 1 plus delta x. So that means you take this and you substitute it everywhere you see an x, right? Does it say f of anything down here? Oh. Okay, expand and combine like terms then. All right, so that would be what? 1 minus 2 delta x plus delta x squared. You guys expanded binomials before. Don't forget the middle term. Plus 1. Negative 1 quantity squared is 1. 1 plus 1 is 2. So minus 2. All over delta x. Limit. Combine like terms in the numerator. What do we got? 1 plus 1 minus 2. Well, they add to 0. And then every term in the numerator now has a delta x, which should happen if you do this correctly. All right, what would that be? Delta x squared minus 2 delta x all over delta x. Are you guys okay factoring delta x out of everything? We're okay writing it like that? Or do we need to factor the numerator and then cancel that way? Are we okay doing this? We're okay? All right, let's see what's left. Limit delta x goes to 0. We have a delta x left and a minus 2. Using parentheses because there's 2 terms left. Can we directly substitute 0 now for delta x? You bet. 0 minus 2, that gives us negative 2. Did we get a negative answer like we thought we would? You bet. Okay, that's good. Questions on this at all? Algebraically, our struggles are going to be our algebraic struggles with math, right? Evaluating a function at 2 terms. We're going to struggle with that a little bit. Mr. Bonley, is there a way we could do this problem and then get like a general term and then substitute 0 and negative 1? There will be, yes. Next one, find the equation of the line that's tangent to the graph. Get started this, if you would, please. See what you can come up with.